And let's start with like a vocabulary check. And the vocab check corresponds to what's going to happen at the bottom of the page. So if it's not a thing that you know off the top of your head, you will in a few minutes. If I say the word quadratic function, what does that mean? Yeah.
I was gonna say like x squared.
Yeah. X squared is like the prototypical quadratic function. Let's see, quadratic is like quad from the Latin for square or something. So it's like a squarish function. It's a function that has to do with squares. And in order to motivate these things, let's even just like do a very light physicsy example. Let's suppose you go to the top of Hibbard Hall, you're carrying a bowling ball. You go to the edge of Hibbard Hall and drop that bowling ball off. Let's answer some questions about this. Maybe let's just answer the most obvious one. How long is it going to take for it to land? And I have assorted the height of Hibbard Hall here to be like 25 meters up. I haven't measured it. There are actually some extra credits in this packet that'll come up later on where you will determine the height of Hibbard Hall by making some indirect measurements. Let's do this then. So you go up to the top of Hibbard Hall. So the initial height is 45 meters. I'll suppress the units for this computation. Acceleration due to gravity is minus 10 meters per second squared, about. So, as a consequence, like there would be a square contribution coming from that. There's no initial velocity, so there's no t at all.
So where are you getting the 5t squared from?
Yeah, so here's a physics and calculus aside. Near the surface of the Earth, the acceleration due to gravity is about negative 10 meters per second squared. And depending on, I mean, people would rather see that as being like 9.98 or something. I think that's closer to truth, but I'm happy with this. If you think about what happens when you do the differential calculus to translate this into what that contributes to the height function, you'll wind up with that 10 getting divided by 2. So you'll have a minus 5t squared.
So meters over second squared, or?
Yeah, because that's the unit that acceleration should be in. So position, height will be in meters, velocity will be in meters per unit time, because that's like the rate of change. So acceleration is the rate of change of velocity, that should be meters, it's the change in velocity over change in time, right? That's what acceleration means. So it'll be meters per second. Cool. Feel okay? Let's do. All right, so with that model, which now I'll just take as given, let's answer the question, when does this bowling ball land? And let's just start by translating that to an equation. What's it mean to land?
For the height to equal 0.
Like 0. Yeah, great. Cool, so ball hits ground, the ball lands. That means that the height is equal to 0. I want to determine when. That should tell you I need to solve something for t. So, let's do it. I want to know when h of t equals 0, so that's 45 minus 5t squared equals 0. That looks like an equation that could probably be solved for time, right? Right, there's only one t, so it should be. Do it. How would you want to do that? Give me like a reasonable first step. Yeah.
Subtract 45. So negative 5t squared equals negative 45.
Nice. How many people would rather have added 5t squared to both sides?
Isn't it negative 10t squared?
Ooh, so you're thinking because of this 10, that should be 10?
Yeah.
Yeah, cool. So here's a thing that will happen during the course of calculus. So the fact that the acceleration due to gravity is minus 10 meters per second squared, that'll tell you that like the velocity as a function of time will be minus 10t. And the units will be meters per second. Another bit of calculus right here, if you like. You differentiate again. A thing that you'll learn called the power rule will tell you that the power on that t should go up. This is not things that will happen in the content of this class, so this is absolutely a tangential aside. There will also be like a 1/2 that appears. So that's why it becomes a 5. So like, all that is not this course content. I wanted that formula to just be a black box. But like, we've pulled back the curtain a lot. Folks feel okay? And there will be things that I do wrong today, I'm sure. Because I do things wrong every day. So there's the thing we want to solve. We've made progress. What seems like a good next step? Cool. And negative 45 divided by negative 5 is? Good. Yeah. Double negative cancels, and yeah, 45 is 5 times 9. All right, so I'm now at t squared equals 9. What next? Square root. And in general, just the mathematics says that when you undo a square with a square root, you'll get a plus or minus. So I'm going to put the plus or minus root 9, that's plus or minus 3. And maybe I'll put the units back in. And I like harped on that plus or minus, but does the plus or minus actually matter in this example? Yeah, why not? Yeah. A negative time would be like before you drop the bowling ball off a pivot. And if you like, when you talk about domains of functions, if you have a function that's given by like a formula modeling something real, think about the inputs that actually have this thing having reasonable behavior. Negatives aren't even in the domain. Gesundheit. So, when does the ball hit ground? Just at t equals 3 seconds. Because the negative time value is not reasonable. Cool. Nice. So all that done, what's the point here? If you want to do like even just very basic physical studies, you need to think about functions that have to do with t squared. Because when you have a constant acceleration due to gravity, you'll wind up with position having this squared one. And of course, like, squares show up all over the place. If you're doing anything geometric that has to do with area, there will be squares involved. Like cost analysis, those will involve like quadratic functions. So let's study them. What's the name for these things? Quadratic functions is the name. A quadratic function is any function that can be put into the form ax squared plus bx plus c, where a, b, and c are constants. I don't know, like, that seems like a function that's at most as complicated as x squared, right? Like, x squared is the most complicated thing you see there. So that's a quadratic function. A quadratic equation is any equation you can put in the form 0 equals ax squared plus bx plus c, and our goal is to study those functions to solve those equations. Seems reasonable? All right, so here's one. Let's suppose, I've crossed that out because like it's an example that'll give different behavior than I want to see today. X squared plus 2x minus 2 equals negative 1. That's a quadratic equation. If I asked you to solve it, could you use the same technique as we just used? Not like immediately, because there are like 2 places where I see an x. It's like, I don't know, you add 2 to the other side. But then what are you going to do? There's like an x squared plus 2x. So you need to do something else, yeah.
Factor out one of the x's.
Ooh, like there's a factoring game that seems relevant. And we will do some factoring. Factoring is most useful if you see like an equals 0 on the other side. Because then like, we'll see why. I don't know, let's hear it. Like, there's an answer on the next page, which is like the problem of having these prepared notes. Like that would be an excellent tangent to go down right now. But what other ways would you want to solve this? If I just handed this to you and said solve this equation, what would you want to do?
Quadratic.
Yeah, there's a thing called the quadratic formula that just solves degree 2 polynomial equations. So for now, let's treat that quadratic formula as like a magic black box that like solves these things. Let's use it. I won't tell you why the quadratic formula walks yet. There's an extra credit where you see why it walks. And do it. Theorem. The quadratic formula says that the solutions to the equation ax squared plus bx plus c are given by, I don't know, how many people have the quadratic formula on the top of their head? Let's hear it.
Negative b plus or minus the square root of b squared minus 4ac and all that is over 2a.
Nice, that was very fast, but I'm writing it down right now. Cool. So if you ever want to solve an equation that looks like a bunch of square stuff set equal to 0, there's a black box that tells you what the solution to this thing is in terms of those a, b, and c. And so let's use that real quick. Let's try to solve this same equation. X squared plus 2x minus 2 equals 1. Same as on the previous page. Can I just use the quadratic formula on that as is?
No.
Why not? I agree, but why? Yeah,
That's b equals 0.
yeah, I need an equal 0. But I can get an equal 0 on the other side, right? What do I need to do that? Yeah.
Subtract 1.
Subtract 1. I had lost the sign in my head. Cool, so do that. X squared plus 2x minus 3 equals 0. And let's go ahead and do that. So, and like, usually you wouldn't explicitly right now say what the a, b, and c are, but let's just do that for the sake of completeness. What should I use for a?
1.
Yeah, because it's 1x squared. So there's my a. B? C? Is that one? Alright, so let's just use it. By the quadratic formula, this says that x should be negative b plus or minus the square root of b squared minus 4 times a times c all over, close parentheses, Chris, 2 times a. You know. So, in some sense, there's an answer. I think if you like gave me this as your final answer on an exam or something, I'd say, well, you need to finish simplifying this. So let's finish simplifying out this and actually work out what it is. So, and I don't know, how many people as soon as they see something like that would immediately just take out a calculator and do it? That's fine. I'm gonna do it by hand this time because like I know in advance the numbers will walk out not so badly. I picked them. So I'm gonna work it out. So let's just compute it. If you wanted to compute this by hand, what seems like a fast good thing to do? Yeah.
I guess just sort of start with the exponents as that's first order of operations. So let's choose for the 4.
Cool. That'll be 4. Maybe I'll do that at the same time. What's negative 4 times 1 times negative 3?
Negative 8.
12.
Not 8, not negative 8.
Right. 4 times 3 is 12, and you lose the sign. The signs cancel. So let's do that.
Oh wait, I thought C was negative 2. So, oh.
Because I had to get a 0 on that side.
Oh.
Yeah. So, going through. Negative 2 plus or minus square root. 2 squared was 4 plus 12. All over 2. Keep on going. What next? Yeah.
Then you add the 4 plus 12,
Cool. What'd you get?
16.
Nice. And now you see that I've actually rigged this example so the number walks out nicely, because what's the square root of 16?
4.
Alright, and now we can just work out what that is. Negative 2 plus 4 is 2, and then I divide by 2, so 1. Negative 2 minus 4 is negative 6 divided by 2, so negative 3. I feel okay? Alright. And how many people, like, are sufficiently obstinate, independent thinkers that they said, screw it, I'm not going to use the quadratic formula on this, I'm going to factor. Oh, alright. Here's one thing that you can tell as soon as you see those two answers. Quadratic formula always works, but whenever you get just nice integer values, you know immediately you should be disappointed in yourself, because it means you could have factored this, and when you can factor it, the arithmetic works out easier. So, it's exactly too late to know that though, right, because we're done. And, with that in mind, I think I want to, well, maybe I'll see what people want. I want to pause for a moment, have you all solve that using the same technique. Maybe I'll see what people think. We're 20 minutes in. Do people think they benefit from doing one more example? Okay, cool. We won't. So, cancel that. I won't have you do that. Instead, well, no one's hands with that, right? You look at me like I'm crazy. Do people want me to spend the time? Okay, cool. For you, on your own time, use the quadratic formula. Do that. If you did, you'd wind up getting integer values again. So we can play this game called factoring. So let's solve the same equation using a different technique. Let's factor it, and while I discuss like what factoring means and the strategy to do it, I'm going to write more than you probably would usually when you'd want to factor, because I want to explore the idea. So what would it mean to take this thing and factor it? When you factor something, you realize it as something times something else. Right, like 6 factors is 2 times 3. Well, if I want to find these two things, eventually I need an x squared to show up. X squared is x times x, so I'm going to need an x in both pieces. And I don't know what goes in those blanks. For now, just for the sake of referring to them, I'll call the things in those blanks a and b. So I want to like find the values for a and b that make this equality true. And yeah.
Isn't it numbers that add up to b but multiply to c?
Yeah, it is. And let's see why. The reason for that is if you FOIL this out, let's see what you get. So FOIL is an acronym that's forced, outside, inside, last. Multiply the forced terms together, you get x squared plus outside terms b times x plus inside terms a times x plus last terms ab. So x squared plus a plus bx plus ab. And now we see exactly what you said. A times b needs to work out to be minus 16. A plus b should be 6. Cool, so I need two things that multiply together to be minus 16, add together to be 6. There are only so many integers that multiply together to be minus 16, so we can like track them all. But let's start with thoughts for things that seem like they'll be good choices first. Yeah.
8 and negative 2.
I hear an 8 and a negative 2. And let's just check it. 8 times negative 2 is 16. That's good. 8 plus negative 2 is 6. Oh, that's what I wanted there. Nice. So it looks like A equals 8, B equals negative 2. So, how does this factor? This thing factors as x plus 8 times x minus 2. Feeling good? And now that we factored, instead of setting the original thing equal to 0, let's set the factored thing equal to 0. And there's a good reason to factor, especially when you set something equal to 0, because what's the only way a product can be 0? One of them has to be 0. And that's something special about 0. This couldn't be a 5 over there. If that were 5, then there are lots of different ways to multiply things together to get 5. So either x plus 8 equals 0, or x minus 2 equals 0, so both of those are easy to solve now. X equals negative 8, or plus 2. Cool. And so here's the takeaway. Quadratic formula always works, but the arithmetic gets ugly quickly. You can't always factor, right? maybe there aren't two things that multiply together to be, if that 16 were 15 instead, you're kind of screwed. Yeah. But when you can, factoring gives you an easier way to get a solution. Folks with me so far? All right. One last thing I want to hit in this particular discussion, and this is the idea of completing the square. So, if I say completing the square, how many people have an idea of what that means already? How many people continue to have an idea what that means if I ask the follow-up of what does it mean? Okay, cool, then it's definitely worth talking about. Let's complete the square. And before we complete the square, let's motivate why complete the square by thinking about graphs. So here's an easy task. Let's suppose I asked you to graph that. Y equals x minus 2 squared minus 30. How would you graph it? So you'd start with x squared, and then you would... No, we'll do that next. This is something you can graph by transformations, right? So, how would you transform the graph corresponding to this?
It's like an upwards parabola that's moved to the right 2 and down 3.
Cool. Right 2, down 3, but otherwise it looks like x squared. Right 2, down 3. Otherwise it looks like a parabola, and if you plug in x equals 0, you'll find out it goes through 0, 1. So I just want to have that much of the graph correct. Cool, so you can graph it. In order to motivate completing the square, now let's FOIL. If you FOIL to expand this out, let's see what we get. How many people need a quick detailed reminder of how to expand this out? Cool, then expand this out. Compare it with those around you. Let's see what we get. And when you do compare with those around you, do so in an exaggerated, cartoonish way so I can clearly tell if people are feeling done.
Okay, so, what is that?
Oh, sorry. Cool. All right. What'd you get?
I also got x squared minus 4x plus 1.
Groovy. People feel good? All right. So what if I want to ask you now, graph for me x squared minus 4x plus 1. Well, this is like a silly question, right? We've already done it. X squared minus 4x plus 1 is equal to x minus 2 squared minus 3. What will it look like? It'll look like that. So here's the point of this exercise, which maybe felt roundabout. So it's easy to go from here to there, FOIL. If you could figure out a way of starting with x squared minus 4x plus 1 and turning it back into something that looks like this, that gives you a way of graphing it by transformation. That's what completing the square is. Completing the square is the act of taking a quadratic function, ax squared plus bx plus c, and realizing it as something that looks like x squared stretched and maybe flipped, and then shifted right or left, and then shifted up or down. And on the next page, we'll talk through a strategy for completing the square. There are a few. Let's talk about why. So we've already seen one. That is easy to graph. So if you want to graph one of these, if you can turn it into that, you can graph it. Anything you can read off from a graph, you can then read off from this. So let's take a look at that graph. Let's suppose I asked you what's the minimum value this function takes? Then what would you tell me?
-3.
-3. And what's the x value that produces that minimum?
2.
Nice. So like, those entries tell you optimization questions. If you want to make an optimal choice for a model that comes from a degree 2 polynomial, if you can complete the square, you can just read them off. And in fact, let's see, if I gave you something that looked like x minus 2 squared minus 3 equals 0, and asked you to solve that, and told you were forbidden from using the quadratic formula, could you?
I don't think so.
I think you could. There's only one x. So you could add the 3 to the other side. And I'm not going to do any more than that. You can undo the square with the square root. You'll get a plus or minus root 3. And then add 2 to the other side. Oh, cool. So you can solve things by completing the square. And in fact, the reason that this is true is because of completing the square. There's a sales pitch for extra credit. Derive the quadratic formula by completing the square and see what you get. All right, so there's like the sales pitch for why complete the square. I guess the question that's left is how to complete the square. And I mean, I don't know, how many people already have some memories of strategies that complete the square? Cool, then excellent, this will be new. So, I want to talk about a very ad hoc strategy for completing the square. It's a strategy that will follow from just thinking about what you want to get and making that happen. So here's the way I'll think about completing the square. I want like an x plus b squared to show up. So let's just like see what x plus b squared looks like when we FOIL it out, and see what we can do to arrange that that flavor object shows up in our analysis. So FOIL out x plus b squared, let's see what we get. X plus b times x plus b. First term is x squared, outside, inside, plus bx plus plus 2bx plus last term, b squared. And that b could be any parameter we want. We get to choose b. So here's the strategy. If I can start with a thing that I'd like to do completing the square to, if I can find something in there that looks like x squared plus 2bx plus b squared, then I could just replace it with x plus b squared. They're the same. And let's try to do that in practice. Let's try to complete the square to this. And to do that, I'm going to look at that. I'm going to try to identify pieces that do and don't look like x squared plus bx plus c, and see what I can do to make them look more like. So what's the first difference I see? I see a negative in front of the x squared. I just see a 1 in front of the x squared. What seems like a good way of fixing that?
Multiplying both sides by -1.
Yeah, great. I see a negative. I don't want a negative. How do you make a negative positive? If you multiply both sides by -1, that'll do the job. So what'll that do? That will give me minus y, and I want to hold on to this minus y because it'll like be important at the end, equals x squared minus 6x plus 3. I have to multiply everything on both sides by -1. And this like constant term, for now I just want to ignore it. I'm going to move it to the other side just so I can ignore it for a bit. Negative y minus 3 equals x squared minus 6x. All right, so I see plus x squared. I see I need to see a 2bx, and I see a 6x right now. Oh, wait. Is there a choice of b that would result in 2 times b being -6? Yeah, what's that choice of b?
-3.
Nice. I think I see a choice of b. I think that I see b equals -3 seems useful. Ooh, but I also need to see a plus b squared. Do you see a plus -3 squared showing up there? Could you like make one show up? Yeah, how could you do that? So I need to see a +9. Could I just add 9 to both sides? That'd do it, right? Let's do it. So I want to get x squared plus 2bx, so that's 2 times -3x plus -3 squared to show up. I don't see this -3 squared, so let's add 9 to both sides, because 9 is -3 squared. So, minus y minus 3 plus 9, I'm just adding the 9, I'm not simplifying yet, equals x squared plus 2 times -3x plus 9. And this is an equivalent equation to the one we started with. And the whole damn point of doing all this is that stuff on the right-hand side of the equal sign. That's a perfect square now. b is -3. That is x plus -3 squared. So let's just write down what we have so far and see where to go. -3 plus 9 is 6, right? So minus y plus 6 equals x minus 3 squared. And I started with something that said y equals, let's turn that back into y equals. So I guess like now we just need to get y back on its own. So subtract 6, and then divide by -1. Cool. Subtract the 6. Minus y equals x minus 3 quantity squared minus 6. Multiply both sides by -1, or divide both sides by -1. Those are both the same. So y equals negative x minus 3 squared plus 6.
Where's the x plus 3 because the negative got?
Ooh, you're worried about this -3?
Yeah.
So let's see, this negative sign, when I multiply it by both sides, so I need to multiply x minus 3 squared by a negative. So that's where that negative comes from. And -6 becomes plus 6. Let's investigate like whether that should or shouldn't be the same thing as like x plus 3 squared. Are they the same? And I don't know, like one way of investigating that is like that's a downward parabola, that's an upward parabola. It's like you can't distribute the negative sign through the squared. Because right, like squares kill off the negative once the negative's inside of the square. Yeah.
So what exactly is the point of completing the square? Just because it seems like it's such a it seems like it's so much more complicated than just a complete quadratic formula.
Cool. Well, I'm actually going to challenge the idea that quadratic formula is not complicated. Because what if I asked you why is the quadratic formula? That's like hard, right? This had a lot of like moving parts, but each individual step was hopefully reasonably motivated. I wanted to get something like that to show up. And once you can complete the square, you can just get the quadratic formula. And you can get way more, right? Like, we can graph this now. That -3 became a -4 accidentally. Replace that with a 3. If I asked you to graph this, you now just can. Because we've now established that is the same as negative x minus 3 squared plus 6. So we can just graph this thing now, which we couldn't before. Not without like plugging in a bunch of points and hoping we've plugged in enough to get the right pattern. So let's even graph it. You want to graph this thing, you'd start with an upward opening parabola, and then what would you do to it? That minus sign will flip it, so it's upside down. and then you'll go
Right 3, up 6.
right 3, up 6, and then it's downward opening parabola. 1, 2, 3, 1, 2, 3, 4, 5, 6. Downward opening parabola. And you can check the y-intercept is at y equals -3. And there's your graph. That means I can also optimize using this. In looking at this graph, does this have a maximum value or a minimum value or neither?
Maximum.
There's a maximum. No minimum, it goes infinitely negative. What is that maximum value? 6. That tells you the max. What's the input that produces the maximum value? X equals 3. So here's like the reason that completing the square is powerful. It lets you do absolutely everything that you would do with transformations with any quadratic function. And all of the things you know about quadratic functions, all these like quadratic formulas, the vortex formula, any like fancy fact that you know about quadratics is true because of completing the square. And what we just did felt complicated, but I think it'll feel less complicated if we do one more example and like actually write less. Like there's lots of words written there.
Yeah, I just really struggle with processes that have like a ton of steps, and even if it's the steps themselves are simple, that it's just like I don't know, I find a 5-step plan where the steps are complicated way easier than a 20-step plan with 80 steps.
Yeah, so here is the step. Find this showing up somewhere. So, let's try to run that same example on this. And we'll start with the most complicated piece and work our way down. So, I see a 2 in front of the x squared. I don't want to see a 2 in front of the x squared. This says I want to see a 1 in front of the x squared. So what should I do?
Find everything on both sides.
Divide by 2, great. That'll give me 1/2 y equals x squared plus 3x minus. Now I have to make a decision, decimals or fractions? Decimals, fractions.
I think you already wrote the fraction down, so.
I guess there's already a fraction. I don't want to change that -1/2 to -0.5. All right, so I guess I've already made my decision. If you don't want fractions, you can write your decimals. And in fact, I'll even do it. 0.5 equals x squared plus 3x minus 2.5.
25y.
Yeah, that is very important, isn't it? Without that, like, I need that y so I know, like, how to put things back. All right, so. Inspired by what just happened, what would you want to do next? I want to see something like that showing up.
Add the 2.5 to the other side.
Yeah, that plus 2.5, that constant, like it's only going to get in the way right now. So let's get it out of the way. So that I just see these two most important terms. 1/2 y plus 5/2 is equal to x squared plus 3x. Oh, and I don't think I'm supposed to be double spacing. I think I'm shooting myself in the foot there. Anyway. All right. And at each step, at each manipulation, look at the goal. There's the thing I want. I see my x squared, that's great. Next I need to see a 2bx. Do I see something that could be 2bx sitting there?
1 and 3?
I see a 3 times x. So could I write 3 as 2 times what?
2 times 1.5.
2 times 1.5. I'm going to write that as 3/2 because if I write 2, 1, 1/2, then like I'll get very confused.
Yeah.
So let's do that. It looks like I'm going to use b equals to 3/2. So 1/2 y plus 5/2. I'm going to give myself some space right here. Equals x squared plus 2 times 3/2 times x. All right. Well, now I know that b is 3 halves. I know that I need a b squared to show up. What is b squared? I mean, like, the cheekiest answer is 3 halves quantity squared.
3.
No, that's 2 times 3 halves. Say that.
1 quarter, or 9 quarters.
9 quarters, which is 2 1/4. Yeah, yeah. So I need to see a plus 9 over 4. Oh, that just means I need to see a plus 9 over 4 over here. And at this point, the hard part of completing the square is done. All that stuff we did is because now all that nonsense on the right-hand side is a perfect square. It's x squared plus 2bx plus b squared.
So we get 9 over 4 because that's the square root of 5 over 2? Or,
3 over 2.
oh, okay.
So you figure out what b is. In the foiling formula up top, you see b squared, so you need b squared to show up. Yeah.
I'm confused exactly how you figure out what D is. How do you figure out like D is?
Cool. So I got the x squared to show up, which makes me happy.
Yeah.
I see a 3x in what I have.
Yes.
In the thing I want, I see a 2bx.
Okay.
So you say, well, I need that 2bx to be 3x.
Okay.
Yeah, so like the x's cancel, 2b equals 3, so b has to be 3 halves.
Okay.
Helpful?
Yeah.
Cool. Nice. So let's now finish this up because we're done with all the hard walk. There's like the light steps where we put things back together. That piece is a perfect square. So I'm even going to color code just a little bit. So the next line, you see that perfect square showing up. So left-hand side I'll leave alone for now. 1/2 y plus, oh gosh, we should combine those fractions, right? This isn't like an important step, but it's a step you should do. How do you feel about adding fractions?
Pretty good.
Anyway, how do you add fractions?
Get the denominators the same and
Get the denominators the same, then you can add the numerators. Between those two, what's a common denominator?
4.
4. So I guess I just need to multiply and divide that one by 2, giving me 10/4. 10 plus 9 is 19. So that's like really fast, but like adding fractions isn't the point of what I'm doing right now. That was just something I had to do. Equals. Now is the point that like matters. That's a perfect square. That's x plus 3 halves quantity squared. And now I just need to get y on its own, and then I'm done. In fact, I could call myself done right now. I have completed the square. I should just probably get it into the form y equals. So y equals, subtract 19 over 4. X squared plus 3 over 2 squared. Then I'm going to subtract 19 over 4. I have an erasable pen for a reason, because I didn't write the 1/2 either. There, now there's the 1/2. How do you get rid of that 1/2? Multiply both sides by
where are you
2.
getting the x squared from? Where it goes from x?
This x squared?
I mean, well, you go from x plus 3 over 2 squared to x squared plus 3 over 2 squared.
No, I didn't. Let's multiply both sides by 2. Cool. Nice. So, there's the act of completing the square. There are multiple approaches, but I think I like this one because it is very ad hoc. Like, you don't have like an algorithm in mind, you just have a goal. Get the quadratic you have to look like that. Once you get it to look like that, use this fact, which is just foiling, and then put everything back together. And in fact, here's the first thing we'll do next time. Do you think I could have done that for like any coefficients instead of 2, 6, and -5? I could have done that for any coefficients, right?
Sure.
What we'll do next time is we'll do that for any coefficients. I will give you a formula for this week's test. We do have a test tomorrow. On Monday, we will do that thing that I just said. Yeah, let me hit the stop recording so that like